There are these invisible forces, right, all around us, like ultraviolet radiation, UV light. It comes from the sun, sure, but also industrial processes. Lots of places.
Yeah.
And it can be pretty powerful, even, dangerous.
Definitely.
So now imagine trying to detect that invisible light reliably, accurately, but in places that are just incredibly hot. Super extreme conditions where, frankly, most sensors would just, melt or fail completely.
Yeah, that's a huge challenge. A hidden one, mostly.
Right. But what if the answer involved, like, one of the toughest materials we know?
Okay.
Welcome to the deep dive. Today, we're really getting into a breakthrough in UV photodetector design. And this one, it kind of flips everything on its head.
Sounds interesting.
We're talking about this cutting-edge material.
Yeah.
The idea is it could totally revolutionize how we sense UV light, especially in those really harsh environments.
Okay.
Our source material digs into how scientists are using diamond, super tough diamond, but combined with platinum.
Like the metal?
Yeah, exactly, the precious metal, to create these sensors that don't just survive where others fail. They actually seem to thrive when it gets incredibly hot.
Okay, that is unexpected. So in this deep dive, you're going to learn about the big problem these new detectors are solving, which is basically reliable UV sensing in really hot, tough conditions where, the usual tech just gives up.
Right.
We'll unpack how these platinum-embedded diamond nanowires, how they actually achieve this amazing performance.
Yeah.
It seems counterintuitive, right?
Totally.
And then, we'll look at where this could actually be used now and, down the road. What's really cool is how they've taken diamond, which is great for UV anyway because it's an ultra-wide bandgap semiconductor.
Okay, ultra-wide bandgap.
Right, perfect for high-energy UV light. But they've figured out how to get around its biggest weaknesses, especially the heat problem.
So let's paint that picture a bit more. Why is this robust UV detection so critical?
Well, think about it.
You've got industrial monitoring, right? Like processes generating immense heat. Or maybe defense systems they need to work flawlessly no matter what.
Absolutely. Critical stuff.
And space exploration, obviously. Huge temperature swings, radiation. It's brutal. But the sticking point, as you said, is that traditional UV detectors, they often struggle. Or they just die when the heat ramps up.
They weren't really built for that kind of thing.
It's like your phone overheating and shutting down, but way more critical.
Exactly. And the specific scientific reason, the hurdle, has always been this. Diamond should be great. That ultra-wide bandgap we mentioned.
Yeah.
Perfect for UV. But its actual effectiveness, especially when it gets hot, was always limited.
Okay, why?
Mostly because of something called surface oxygen termination.
Surface oxygen? What now?
Termination. Think of it like getting a layer of fog on your glasses. Oxygen atoms basically stick to the diamond surface and create this barrier.
Yeah.
And that barrier stops the diamond from, seeing the UV light properly. It drastically cuts down its photoresponsivity, its ability to turn that light into an electrical signal. The signal just wasn't strong enough, especially hot.
Gotcha. So the oxygen was kind of blinding it.
In a way, yes.
Yeah.
Especially under heat.
But, okay, this is where the breakthrough happens, right? This team, led by Professor Dongming Sun, University of Science and Technology of China, Shenyang National Lab for Materials Science, and others, they found a way around it.
They did.
And their solution, it sounds almost simple when you say it, but it's clearly not. They're using single crystal diamond nanowires.
Nanowires, right. Tiny.
Like incredibly thin wires, thousands of times thinner than a hair, but each one is a single perfect diamond crystal. That part, the single crystal integrity, seems really important. But here's the twist. They embed these wires with platinum nanoparticles.
Platinum again, okay.
Yeah. So diamond nanowires with tiny bits of platinum scattered inside them. Seems straightforward, maybe, but the effect is apparently profound.
It really is.
Okay, let's get to the performance then. The numbers. Because this is where it gets, really wild, right? What these things can actually do.
Yeah, this is the astonishing part. Let's talk responsivity first.
Okay, remind us what that is.
Sure. Responsivity is just how good the detector is at converting light into electricity. Like how much electrical current you get out for a certain amount of light hitting it. Measured in amps per watt, a watt.
Got it. Amps per watt.
So these new nanowires, at room temperature, under specific UV light, 220 nanometers, they hit 68.5 RUA.
Which sounds good. How good is that?
It's very good. But here's the comparison. That's about 2,000 times higher than what you get from those older oxygen-terminated bulk diamond devices.
2,000 times?
Yeah. 2,000. A massive jump. But wait, here's the truly crazy part, the counterintuitive bit.
Okay.
Normally, electronics hate heat,
Right.
Performance degrades.
Always.
Their responsivity actually increases significantly with temperature.
Wait, what? It gets better when it's hotter.
Exactly. It reaches this staggering figure 3098.7 year OU at 275 degrees Celsius.
Whoa. Okay, that does flip things on its head. Heat makes it more sensitive?
Precisely. This is revolutionary for high-temperature sensors. It uses the heat to its advantage.
That's incredible. Okay, so it's super sensitive, especially when hot. But it's not just about how much light, right? It's about picking out the right light. The source mentioned excellent spectral selectivity.
Correct. And solar blind UV detection.
Solar blind, what does that actually mean for, us non-specialists?
Good question. Solar blind basically means the detector is specifically designed to see certain UV wavelengths off of the really short, potentially harmful ones, while completely ignoring everything else, especially visible light from the sun or, room lights.
Ah, so it's not getting swamped by background light.
Exactly. That visible light would normally just drown out the faint UV signal you're trying to detect. This precision is vital if you want reliable detection in the real world.
Makes sense, and the numbers back that up.
They do. The UV to visible light rejection ratio, how well it ignores visible light compared to UV, is 550 at room temp. Pretty good. But at 275 degrees C, it jumps to 4303.
Wow. So it gets even more selective at high temperatures, too.
Yeah. Much better at picking out just the UV it needs to see, even when it's hot and bright.
Yeah.
Crucial for space or looking into a furnace, that kind of thing.
Okay, sensitivity, selectivity. What about just holding up over time? You mentioned harsh environments. Stability must be key, right? It can't just work great for 5 minutes.
Absolutely critical. And the news here is really good, too. They tested this. The devices stayed stable, performed reliably, even after running for 24 hours straight at 275 degrees C.
24 hours, that heat. Okay.
And maybe even more impressively, they stored some devices just out in the open air for 3 months, and they still work perfectly afterwards.
Yeah.
Retain full functionality.
3 months just sitting there, that really speaks to robustness.
It does. It suggests they could last a long time in those tough deployment scenarios.
Yeah.
Aerospace, heavy industry where you can't just pop in and swap them out easily. Failure is not an option there.
Definitely not. Okay, that reliability sounds amazing for something so, well, nanoscale. Which brings me to the how. How on earth do they make these things? Embedding tiny platinum particles inside perfect diamond nanowires sounds incredibly tricky.
It is. It's a really meticulous, carefully engineered process. Our source calls it a unique 4-step fabrication process. Precision is everything.
Okay, walk us through it. Step 1.
Step 1. Prepare the basic diamond nanowires, the DNWs, these super thin single crystal structures we talked about.
Got it. The diamond wires.
Step 2. Deposit a very thin film of platinum onto the surfaces of these wires, like spray painting them with platinum, but way more controlled.
Okay, a platinum coating.
Step 3. This is clever. They use thermal dewetting. Basically, they heat the platinum film up just right so it sort of beads up. It breaks apart from a continuous film into tiny, separate, uniformly distributed platinum nanoparticles, all sitting on the surface of the diamond nanowires.
Ah, okay, so heating makes the platinum form tiny dots.
Exactly. Uniform dots. And then step 4, the final encapsulation. They use something called diamond homoepitaxial growth.
Homo what now?
Homoepitaxial just means growing more diamond on top of the existing diamond. They carefully grow a new layer of diamond over everything, sealing those platinum nanoparticles inside the nanowire structure.
Whoa, so they bury the platinum dots inside more diamonds.
Correct. And this is key because it locks the platinum in place and maintains that perfect single crystal structure of the overall nanowire. It's this whole controlled sequence that makes it work.
That is genuinely ingenious, like building this tiny, perfect sandwich layer by layer.
Pretty much, yeah, the nanoscale.
Okay, so that's the how. Now, the why. Why does this specific combination diamond nanowire embedded platinum work so spectacularly well? The source talks about synergistic enhancement mechanisms. Sounds like things working together.
That's exactly it. Synergy. There are 4 main factors, and they all kind of boost each other. Teamwork, basically.
Okay, factor 1.
First, the shape itself. The one-dimensional nature of the nanowire. Think of it as a direct highway for the electrical charges, the carriers. They can zip along the wire very quickly with minimal scattering or detours. Much better conductivity.
Like an express lane for electricity.
Kind of, yeah. Second factor, deep-level defects within the diamond itself. Now, usually defects are bad, right?
Usually, yeah, flaws.
But here, These tiny specific imperfections within the diamond crystal lattice actually help. They act like little trigger points. When light hits them, they help generate more charge carriers than the perfect diamond would alone, so boosts the overall sensitivity, the photoresponse.
Interesting. So flaws are actually features here.
In a controlled way, yes. Third factor, the embedded platinum nanoparticles. These little guys do something called localized surface plasmon resonance, LSPR.
Plasmon resonance.
Okay, think of the platinum particles as tiny antennae. When UV light hits them, they resonate like tuning forks, but for light. They basically suck in more light energy and concentrate it right near the diamond interface. Massively boosts how efficiently the structure absorbs the incoming UV light.
So the platinum acts like a light-gathering booster.
A very efficient one, yes. And finally, factor 4, the localized Schottky junctions. These form right where the platinum touches the diamond.
Schottky junction.
It's a type of electrical junction that forms between a metal and a semiconductor. Here, these junctions are really good at separating the positive and negative charges, the charge carriers that are generated when light is absorbed. They pull them apart effectively, preventing them from just recombining and canceling each other out. This boosts the overall electrical output.
Okay, so the junction helps collect the electricity generated.
Precisely. So you've got the wire shape helping charges move fast, defects creating more charges, platinum sucking in more light, and the junctions efficiently separating the charges. All these things work together.
It really is like that orchestra analogy then. The shape, the defects, the platinum antenna, the junctions, all playing their part perfectly together.
That's a great way to put it. It's the combination, the synergy, that leads to this outstanding performance.
Right.
Way better than any single part on its own.
Truly fascinating stuff. So, stepping back, what's the big picture here? What does this mean for the future? Where are we likely to see these platinum diamond nanowires actually being used?
Well, the most obvious immediate applications are definitely those harsh environments we keep mentioning.
Like aerospace.
Exactly. Spacecraft need reliable UV sensors that can handle wild temperature swings and radiation. This seems tailor-made. Also, industrial monitoring. Think inside high-temperature furnaces, chemical reactors, places like that.
Okay. Defense, too, you mentioned.
Yes, definitely defense. Having robust, truly solar-blind UV detection is critical for things like missile plume detection or battlefield awareness systems that need to work reliably under extreme conditions.
Makes sense. And what about the researchers? What are they looking at next? Is it just about making more of these?
Well, there's always optimization. They'll be looking at fine-tuning the size and the spacing, the distribution of those platinum nanoparticles, trying to squeeze out even more performance.
It's just pushing the limits.
Naturally. And beyond just platinum, there's material exploration. Could other metals work? Maybe different combinations or composite structures? Exploring those avenues could open up even more possibilities for diamond-based detectors. It's still an active area of research.
And I keep thinking, what about putting these on flexible materials? Or weaving them into fabrics? Could we see, like, wearable UV sensors for firefighters or hazmat teams, or maybe even smart clothing someday?
That's a really interesting thought. Integrating these robust sensors with flexible or wearable tech could definitely broaden the scope way beyond just fixed industrial or aerospace uses. It opens up possibilities for personal safety, environmental monitoring, lots of potential there, though likely further down the road.
It's amazing, though. We've really taken a deep dive today into how scientists are flipping the script, right? Turning extreme heat, usually the enemy of electronics, into an actual advantage for detecting UV light, all thanks to this clever mix of diamond and platinum.
It really is a prime example of materials science ingenuity, pushing boundaries.
Absolutely. And it underscores that idea that knowledge really shines when you understand it and apply it, you know?
And this work, it just perfectly shows the power of combining materials. You might not expect super hard diamond, precious platinum to get these breakthrough results. Advanced sensing is really moving forward.
So here's something for you, the listener, to think about as you go about your day. How might materials like this, materials designed not just to survive, but to thrive in the most extreme conditions imaginable, how might they change the way we sense and interact with our world, especially the parts we can't even see?
Yeah.
What other impossible environments could become accessible thanks to this kind of innovation? Where else could we turn challenges into opportunities by rethinking the materials we use?